Hey, all, today we're going to continue talking about linear regression. We're going to add to it. We're going to talk about one of the values that we should have seen last time when we calculated regression and what it means. So we're going to use the same example we used last time. This is the exact same example about the age of cars, Toyota Corollas to be specific, within 250 miles of Redlands, California, and the prices that they're advertised for on CarMax. So we went and we calculated linear regression. We did stat, calc, chose option 8, and we should have gotten an output like this, where we chose A as the slope, or I'm sorry, the intercept of our regression line, and B as the slope of our regression line. We calculated R a couple lessons ago. That's our correlation coefficient, regular R. But we haven't talked about this value yet, R squared. And in the calculator, it's a lowercase r, but when we're writing about it and we're talking about it, it's actually a capital R, R squared. And this decimal, we actually will convert to a percentage. So R squared for this is 89.14%. So R squared is what we call the coefficient of determination. Like I said, we use capital R. It is the percent of the variation in our dependent or response variable that we can attribute to, or that we can say is accounted for by the independent or explanatory variable. So let us put it into the context of our problem. Our R squared value, we would move the decimal place 2 to the right and make it 89.14%. I guess I didn't need the percent in there. So 89% approximately of the variation in our dependent or response variable was the price advertised for our vehicles. So our vehicles aren't always going to be the same price based on how old they are. And in our data set, we can see that is true. So we have a couple vehicles that are 4 years old, they're different priced. A couple vehicles that are 5 years old, not the same price. 7 and 8, same thing. Typically, they're not going to be the same exact price for good reason. There are different things that affect the price of a vehicle besides the age. So for us, 89% of that variation in the price can be accounted for by the age of the vehicle. And I made this kind of a fill in the blank because we can sort of use this sentence structure for any time we're trying to explain the R squared coefficient of determination in context. We always want to explain it in context of the problem. What does 89% mean? It means that 89% of the variation in the prices for our Toyota Corollas can be accounted for by the age of the vehicle. So the age of the vehicle is contributing to 89% of the variation in the prices in the vehicles. There's some other things there that will change your price of the vehicle, that will affect what price you would list it for. Some of those things can be whether or not the vehicle has been in an accident, if the vehicle has any modifications done to it. That could be good or bad, depending on how you look at that. Is the vehicle from a state where there's a lot of snow, which means there's a lot of salt on the road, which can cause rust, things like that. I did just want to go back and just reiterate, we can, in this class, be a bit formulaic in our writing. It's not a time to be creative. It's a time to report on what these things mean and what we found. So you can use this sentence structure and just sort of fill in the blank for any time you describe the coefficient of determination. So when I ask you at the end of this to describe a new r squared, you can use this structure and sort of plug in the appropriate variables and r squared value. In the last lesson, or the last two really, when we're talking about calculating correlation coefficients, or when we're talking about writing a linear regression model or regression equation, that's only appropriate if we have linear data, if our data is quantitative, and there are no outliers. Sometimes when we look at a plot, especially when there's a lot of data points, sometimes there are patterns there that are nonlinear, or there are points there that are outliers, or there are unusual things about those plots that we can't see just by looking at the original plot. And so we can plot the residuals. So what we would do here, and we won't do this right now, remember our residual from last time is our observed value minus our expected or predicted value. So we take what did we actually observe to be true and subtract from that what we would expect based on our linear model and when we plug in and make a prediction. If we were to calculate the residual for every data point in a scatter plot, we can create a residual plot. So here we have a scatter plot of years and the men's age, women's age. I forget the context completely of this, but we can run a regression and get a line that looks like it'll go down to the right. Looks like we have linear regression. No real outliers, it doesn't look like. But if we want to be extra sure, we can make this residuals plot. We will take all of our residuals for every point, and that will become our new y value. And now we have this new plot with our explanatory variable and our residuals. It looks much different. It should. We're using different values. But what we're looking for when we want to make sure that we have a good linear regression model, that we've done a good job, it's appropriate to run linear regression, is we want this type of picture where there really is no pattern involved here in where these data points are. The residuals versus plotted with the explanatory variable should look like just scattered points. If you see a pattern, if there's some sort of curve that's defined, if it looks like a straight line itself, if there's this sort of like funneling effect where perhaps some of the residuals are tightly packed. So let's say we have a bunch here and then they sort of really fan out in a like a funneling, then we might want to revisit whether or not we should be doing linear regression or if we've made a mistake in our model. A few other characteristics that might occur. We talked about outliers. Outliers have a large residual, which means they are far above or below the rest of the data set. So this point has a large residual. It's really far above the rest of the data set points. And so calculating linear regression might be a problem, probably is a problem for this data set because this point does not follow the pattern. Points that follow the trend. So this point over here sort of follows the trend of these other points in the data set, but it's really far outside of the data set in the X direction. That is a point that we consider having leverage. If you think about it, when you're opening a door, the further away from the door hinge you try to open the door, the easier it is to open. That's because it has leverage. So it's that kind of idea. This point's really far away. We consider it to have leverage. The last thing would be a point that we consider an influential point. So this point, all the way over here, would have a big effect on the slope of our regression line. If this point did not exist, our line would go somewhere like this, and it would have, I don't know, a pretty smallish slope. However, when we put this point in there, it is going to drag our line downward, which is going to have a big effect on our slope. And so we would say that that point is influential. So just a couple of problems here for you to do, a couple questions to answer. We're using the same data from the end of the last lesson. So if you've already calculated the regression equation, you can use that to answer the first parts about slope and intercept. But then I want you to calculate r squared, and I want you to explain it in context. Remember, you can use the sort of formulaic approach to it that I did earlier, and it will always be acceptable because it will be explaining what does the r squared value mean. As always, please ask me for help if you need it while you're working through this. We'll talk about this together in class. Take your time and good luck.